Okay, we're going to start off today's lecture with the example that we could not finish yesterday. Remember, we were designing a 1-bit full adder, and the truth table looked something like that. You had two variables a, b, and carry in. We completed the truth table for sum and c out. Using those min terms, we came up with two expressions: one for the sum, one for the c out. Then we implemented the logic diagram, which looked like this, and we created a Verilog code for this module, which was basically a full adder. And we did it in two different ways: one with the structural model, and the other one with the data flow model. One of the major differences was in a structural model, you have to declare your wires. So anything that in blue here was wires, all the green were outputs, and all the blue right here were inputs. And then we had these commands for different kind of gates, and we were instantiating sequence doesn't matter in structure modeling, and then followed by the outputs and the inputs in parentheses separated by a comma sign. In a Verilog data flow model, you basically can straight go on to defining your inputs and outputs, and also the data type if there is, and then just use the assign function to come up with to define the Boolean expression for that particular output that you have. I prefer doing it data flow model because there's less number of typing, right? Less amount of typing involved. Okay, and then the example 5, which was linked to this example, where not just we had one full adder, but we're gonna have 4 full adder because we want to add two 4-bit numbers. Okay, so say we had A0, A1, A2, A3. This makes a 4-bit number, and then we want to add with another 4-bit number, and then we want to find out what is the sum, and also we want to find out if there's an overflow or not. We know for a 4-bit number the range is going to be -8 to 7. So here's the truth table. It's the same truth table that we had for the full adder, except for we have one more extra column in there, and that is for the overflow. I also, in the previous lecture, showed you a range which was between -8 to +7. If we take two numbers which are of opposite nature, like positive and negative, if you add them, there will never be an overflow, right? So if you have a positive number and you have a negative number, there can never be overflow, right? Similarly for this combination, 1, 0, all were 0. Adding two opposite sign operands, these are A and B, there will be no overflow. Overflow happens when the two operands are positive. So in this case, two operands are positive right here, and the sum is negative. Sum is negative, so there's going to be an overflow. Your designers, the programmer, they already sat down together and came up with this rule, so we'll just stick to it. The two operands are negative, and the sum is positive. So if you look at it, this one, two operands are negative and the sum is positive, there will be an overflow. For the rest of the other combination, there can never be overflow. Okay? Now once we have the truth table for the overflow, we want to come up with an expression, so we'll use K-map here. So we only have two min terms here. So this is 1 right here, and this is 6, so this is going to be this. Here we have A, and we have B and C in here. So what is going to be the expression for overflow here? So this is going to be A bar, B bar, Cn, plus this one is going to be A, BCn bar. There's another thing, if you notice, we don't necessarily have to come up with the expression with A, B, and C in. We can technically use any of these expressions right here to come up with any of these variables to come up with an expression for overflow. So we always strive to look for different variables which could give us the most simplest of the expression. So notice if you see C in and C out, okay, whenever the number of ones are odd, the overflow bit is high. So this here, the number of ones are odd, the output is for the overflow is high. Similarly over here, when the number of ones are odd, the output, the bit for overflow is high. 1 1, number of ones are even, so it's 0. So what property it exhibits right here? Yes, exclusive OR, right? So I can also write down the expression for overflow, which could be Cin exclusive ORing with Cout. Okay, either way is okay. Just want to show you we could do it different ways. Okay, now we want to make sure, we want to verify that this thing is working. Okay, so we're gonna check here, and we're gonna try this example. It's one of the examples that we did in class in previous lectures. -3 in decimal plus 5 in decimal. We know it's going to be 2. It's a 4-bit number, so 2's complement of -3 is 1101, and a positive 5 is 0101. So I'll just add these 0, carry is 1. You get 1 here. 1 plus 1, sum is 0, carry is 1. And then we get 1 0 here, right? We know this is our carry out bit, and what do we do with the carry out bit? We just ignore it, right? And this is the sign bit right here, and we know this is positive, right? And so therefore it makes a code of 2 in decimal, right? Okay, all right, let's put these numbers here. -3 is 1101, 1101, correct? 5 is 0101, 0101. Okay, Cin going in initially is going to be what? 0 here, right? Okay, all right. So when you have Cin 0, A and B set to 1, what would be the sum here? When you have Cin 0, A and B are 1, 1, 1, 0, sum is going to be 0, and carry out is going to be 1 here, right? So we get 0 here, and this carry out is going to be 1, which becomes a carry in for this block right here. So when we are adding 1, 0, 0, what should be the sum here? Come on guys, you need some energy here. 1, right? All right, so this is going to be my sum here, and carry will be what? 0. Great, fantastic. 0, 1, 1 would make what? Sum is going to be 0, carry is going to be 1. And then 1, 1, 0, you add them, you get what? 0. And then the carry out is going to be? Perfect. Okay, so this is my Cout right here. Notice we are missing our overflow here. And we came up with the expression for overflow Cin exclusive ORing with Cout. What would be Cin here? What would be Cout here? We always look at looking at the most significant bits, and most significant bits are what here? Those are A3 and B3, right? Correct. So if you look at the FA3 block right here, so this is your say this is your C1, this is your C2, and this is your C3, okay, and this is your Cout. So basically you take an exclusive OR gate right here. Okay, the output is connected to the overflow. You have C3 here going in here, and then you have Cout here going into the exclusive OR. We know C3 is 1 because this is 1 here. Cout is also 1. Okay, 1, 1 going to an exclusive OR gets you what? 0, right? So this means there is no overflow, and that's what we were expecting. Okay, so if you try different other combinations, this block diagram, this functional block diagram should be able to tell you what is the sum and also whether there is overflow or not. Okay, I'm going to move on to the next example, which is going to be actually similar example, same example. We are going to come up with a code, a Verilog code. Okay. Okay, all right. So we can have our overflow here. Here. Okay. This is going to be our carry in, which is initially it's going to be 0. Okay. So say this is C1, carry out, this goes here. C1 is connected to C1, is right here. This is carry out 2, say, and then this is C2, and this is your carry out 3, say. So this is your C3, and this is your C out right here. Here, and we came up with the expression for overflow from the previous example. Okay, which would be what? This C out, and what would be the other input? C3, correct. Good, awesome. Okay. All right. This graphic is pretty itself is very detailed. We are going to define our inputs here. So what would be the inputs here? It's the same example. We are taking 4-bit numbers and we are giving user switches, and those that user can turn the switch on and off position to provide with the number, which could be from 0 to 15. So we got, how many inputs do we got here? What are those inputs? Come on. Yes. Correct. So we're gonna have total, if you count, actually we have 1, 2, 3, 4, 5, 6, 7, 8 switches, right? Those switches will be our inputs. We just like in any other language, in Verilog you can also create arrays. Okay, so I'm gonna say A, and then 3, 0. Okay, so we got 4 switches, A0, A1, A2, and A3. And similarly, I can say B, those will be 3, 0. Okay, so B0, B1, B2, and B3. What are my outputs here going to be? Say if I actually add a block to it, something like this. So pretty much on the left hand side are all my inputs, and to the right are all the outputs, right? Correct. So those will be, similarly I can just create an array, say S3, 0, okay, S0, S1, S2, and S3, those 4 bulbs, light bulbs. And then is there any other output do we have here? Yes, overflow. Okay, all right, overflow. I'll just say OF for overflow. Okay, what are the wires here? Would you consider this as a wire? Right? Would consider as a wire. You can also declare it as an output, but are we really interested in finding what is the carryover going from adding 2 least significant bits into the next one? It's not of significant importance. So we just declare them as wire, and they will just carry some signals 0 and 1 depending upon what the logic is, right? And similarly C2 right here, those are all your wires, right? These are all your wires. Okay. Okay, so again I would say C, this is my carry out, and those will be from, so 1, 2, and 3, so 3 to 1, and then I also have C out, Okay, Cn is 0, so we will just declare that Cn is equals to 0. Okay, so we have a set of our inputs, outputs, and wires. Is everybody following this so far? Okay, let's move on to the coding part of it. I went ahead and filled the topology and the top part of it. Notice on the left, the top left, there's a box right here, and there is a coding for it. It's little, we need to complete a little, assign sum. This is the equation that we got yesterday. Sum equals to A exclusive ORing with B and C, and so that is going to be A hat B hat Cn. Okay, and C out was A ending with Cn, A ending with B, and then B ending with Cn, and then OR gate. So all the plus signs are replaced by a vertical line right here. Okay, and then this was the full adder module. So if I ask you, what is this module doing here? Full adder module. It's a 1-bit full adder, right? What is it doing? It's only adding Cn A0 and B0, or it's only adding C1 A1 and B1, right? So we would need how many of these in order to do 2s complement adder, carry ripple adder for 4 bits? How many we would need? We would need 4 of those, right? Correct. So in Verilog, what we could do, we could instantiate this model 4 times. So that would be our goal. Now forget about this part. Now we're gonna start coding for this example right here. We have our inputs here. So here I start my coding. So input, the first one is going to be A, and these are just variable name. It could be A, B, C, or whatever you like. Okay, comma, and then we have the input B. Okay, so these are A0. Let me just also comment it for you. So this is basically A0, A1, and A3. Okay, and similarly these are B0, okay. The outputs here are, we got sum, so S here. So again, this is and then we got the overflow, for which I am using OF. F, and that is our all these set of inputs and outputs. Okay, all right. Now we need to we also had wires right here, so let's declare the wires also. You can say wires wires this carry out, and you can say, actually there's not going to be S here, guys. It's only wire, not wires. Okay. And then one wire for the C out. Okay, all right. Now it's about time for us to instantiate all the models. We're going to start out with the model, the name of the module, which is what? Full adder, right here. Okay, remember this full adder right here. Verilog is a case sensitive language, so you have to write it down exactly as it is. Okay, so full adder And remember, since we are going to be using 4 of them, so we have to give an identifier name. So I can say U0, okay, bracket open. Okay, so this is our, say, FA0. This is our FA1, FA2, or FA3. FA0. Okay, now what are the outputs coming out of the FA0 here? S0. Okay, all right. So S0, S0, comma, C1, comma. What about the inputs? Come on, look at the block diagram. What are the inputs going in? Yes, Sri. So A0, B0. Notice I actually didn't have my CN as a wire. If you like, you can, but since I forgot it, so I'll just say anyhow it's 0, so I can just write 0. Okay, all right. So what is this full adder is going to take here? It's going to replace your sum with S0. It's going to replace your Cn with 0. It's going to replace your A and B with A0 and B0. Okay. You can write the inputs first and then the comma. You have already declared your inputs and outputs, so Verilog would know what are the inputs and what are the outputs. So the sequence really doesn't matter. I can have my inputs here and then I can write my outputs. All right. So we need another one of those, full underscore adder. Okay, and this is going to be FA1. Okay. Now, if you look at your block diagram here, FA1. So I'm just going to follow this sequence. Outputs, which are S1, C2, and then I have C1 going in, and then A0, A1 and B1. Okay. And similarly, I'll do it for the next one, full adder FA2. So this is right here. Again, the outputs are C3 and S2. And the inputs are C2, A2 and B2. Bracket open. Make sure you have a semicolon signs and also close the brackets. And the last one right here, full adder FA3. Okay, so the outputs are S3 and C out here. Okay, and then followed by the inputs. The inputs are C3, A3 and B3. And this is actually your code, which is going to take a 4-bit number and add it. Okay. Notice all of these have 5 variables in there, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. If I just add one more variable to it, if I just say comma C2, what would happen? What do you think? Is it going to throw us an error? Yes, it is going. Yeah, it will going to throw us an error because it can only accept 5 arguments in there. Okay, because that's how your full adder is. Your full adder is only accepting 5 arguments. 3 of those are inputs, 2 of those are output right here. Okay, you'll get a better gain of it when you do the lab. is our code complete or we are still not done yet? Say it again. End module. Okay. Do you want to do overflow as well? Right? Okay. So I can say assign overflow is OF equals to what? Overflow here was what? Cout. And the other input was C3. Correct? So what would be the expression here? C3 exclusive ORing with Cout. And we know in Verilog we replace this with hat. Okay. So this will be C3 exclusive ORing with Cout semicolon, and then we say end module. End module is a one word. Okay, so here is your code for a 2's complement error carry ripple with an overflow detector. Is everyone following me here? Okay. Your best bet is always to come up with a functional block diagram. And if you actually look at your lab write-ups closely, always start with a functional block diagram, because that is where you decide what are your inputs going to be, what are your outputs going to be, and what are your wires are going to be. And then you can just come up with an expression for each. Okay, all right, let's move on to our next example, which is a comparator. We may need to compare the magnitude of two binary numbers to obtain their status. Here the first number may be greater than the second, the two numbers may be equal, or the first number may be less than the second. To achieve this goal, we will need a comparator. So we have two numbers, x and y, and we have three variables. One is g, which is greater, one is e, that is equal, and one is l, which is less. So here we are going to finish the truth table for g here, which is the greater. So x is 0, y is 0, so that is going to be 0, right? This is also going to be 0. Well, here x is greater than y, so this is going to be 1. And here x and y both are equal, so this is going to be 0. What is going to be the expression for g here? X, y bar, right? Okay. I forgot to bring my stencil today, so I'll just manually do it like this. So this is my x and this is my y. So I'll just take care and make a bubble and let's connect this to, this is our g here. Okay, all right, let's do it for equal. 0, 0. What is going to be the output here? 1. 0, 1 not equal 0. 1 and 0 are not equal 0. 1 and 1 are equal, so this will be high. So the expression for that would be x bar y bar plus x and y. And we know this is an expression for x NOR, right? Correct? Okay, all right. So I will take so exclusive NOR is an opposite of exclusive OR, so we need a bubble here. And the outputs, the inputs are going in here would be x and y. Okay, so this is our E. What about L? X, y both are 0, so this is going to be 0. So this will be 1 and this will be 0. X bar y. So I'll just make another AND gate right here. I know this is my y, so I can just okay, and this is my x right here. And we would need a bubble here because it's a x bar y, so we get x bar y here, we get x plus y and on the whole thing, and we get x y bar here. Okay, and this will be our L, correct? Does my logic diagram looks okay? No errors? Okay, all right. We will make a code here as well. So what are the inputs here? Yes, guys, what are the inputs here? Yes, Hunter. X and Y. Good, thank you. What about output? Okay, all right, cool. Okay, what do I need to do next here? Can I go with data flow model here? Right? So what do I do next? Come on. Can I just simply go and assign my output variable and expression? Right? How many of those I would need? One each for G, E, and L, right? So I'll start with G. Assign G equals to, G is X, Y bar. So that would mean X ending with Y. Okay. I would need one for E. So that would be, so exclusive OR is X hat Y. So put it in brackets and then just say in word of that. So that would be exclusive NOR for you. Okay. And then we also do it for less. Assign L. The expression for that is X bar Y. So X bar is here. And then ending with Y. Okay. You don't necessarily have to give spaces between them. The Verilog will always execute the inverter gate, and then all the AND gates, and then the OR gates. Okay. And then in the end we say AND module here, correct? Okay, so that was pretty simple. We're gonna move on to our next example. Is everybody following me? Okay, good. Example number, how much time we got? 13 more minutes. Okay. Example number 3, comparator. 2 vectors each with 4 bits. Now this time we have X, which is actually a 4-bit number, and we have a Y, which is also a 4-bit number. If the first vector is greater, so say vector X 0, vector Y is also 4-bit. Okay. If the first vector is greater than the second one, if X is greater than Y, then comp2 is 1. What is comp2 here? So we get 2 input, which are basically vector A and B. Okay, so X and Y, and then we also have a comparator here, which is 2. So you can say this is your comp 0. This is your comparator 1, and this is my comp 2. Is that okay? So remember, we are using FPGA here, right? Which is field programmable gate array. And I mentioned that in our basis 3 board, we got hundreds and thousands of logic cells inside it. What we are capable of doing with FPGA, we can actually create as many inputs as we like and as many output as we like, given the logic cells, whatever the configuration we have. Okay. When we are actually defining or creating or designing our logic circuit, what FPGA thinks of is basically if you have 3 inputs, so FPGA thinks for 3 inputs there could be 8 possible combinations, 0 to 7, and for each combination this is the output. Okay, so it only looks at that output which is in this lookup table right here. Okay, so we have 4 bits here in vector X, and we got 4 bits in Y. Okay, so in the previous example we only had one bit, x and y, so we had four combinations, 0 0 0 1 1 0 and 1 1. Here if I have 8, so the combinations are going to be from 0 to 255, right? It is easier for us to wire those combinations in the FPGA, and the FPGA would just memorize or just remember for each combination what is going to be the output, and that is what we know as a lookup table. Okay, again, when you start using basis 3 board, you will then get a good hold of it. So this COM0, COM1, COM2 would actually, so say right now all the positions are set to 1, right? 1 1 and 1, and again we have combination 0 1, and they go all the way to 255, right? Because we got to the power 8, 4 here, 4 here, so we go ranges 0 to 255, correct? So what is going to be the output here for COM0? If I ask you, both are equal, right? Okay, the condition was if x is equals to y, then comp1 is going to be, so this is going to be 1 and this is going to be 0. And this is for 255, right? Remember, you getting that? Say for 0, what would be the outputs? Same, right? So this will be 1 and that will be, these two will be 0. And so therefore you will have 256 outputs in your lookup table, each for comp0, comp1 and comp2. Get it? Okay, all right. Going into inputs now. What are the inputs are going to be here? Come on, guys. We need to finish this real quick. So we got x and y, right? And I can just say, I can also write it down as this: 0, x, comma, y. Okay. What about the output? There are different ways of programming. You'll learn different ways. Okay. If I give you a code and if I ask two students to make one, create one, their codes will be different. Okay. So just feel comfortable with whatever way you like to do the coding. What is going to be the output here, guys? Can I make an array here also, because we got 3 light bulbs? So that would be 2 colon 0, and then we have comparator. Okay. Okay, and then what I could do here. So because we have the conditions here, so we're gonna create if and else statements here. So we can begin with saying, let's say initial comp is equals to 3 complement b0. Okay, we want those light bulbs initially to be 0, so we say initial and we say comp equals to 3. Why I'm saying 3 here? Because we have 3 light bulbs. Okay, and this b is the bit. When I say 3 complement b0, I'm setting all those 3 bits to 0. In other words, I'm basically resetting it. Okay, so when you turn the power on of the basis 3 board, all the 3 light bulbs will be off. Okay, and then this one syntax right here, you're going to be using this very often in sequential circuit. That would be our next thing, moving forward to next week. Always at x or y. Okay, what does this means? Whatever is going to be below this line, that condition is applied only when there's a change in the value of x and y. Okay, so if there is a change in value of x and y. Okay. Now here are our conditions. The first one, if x is greater than y, okay, then comp, which needs to be high? Which needs to be high? If x is greater than y, then comp2 needs to be high. So I will write down as 3b0 0. Okay, this is my comp0, this is my comp1, this is my comp2. Okay, so light bulb comp2 will be 1 and the other two will be off. Okay, semicolon. Next one, else if x equals to y. I uploaded one file by the name of HDL operators. In Verilog, when you have two equals to sign right next to each other, means you are comparing the two values. Okay, here we are comparing the values of x and y. So if x and y are same, then comp1 is going to be 1. So, which would mean, now somebody gonna have to help me. What are those bits going to be? 0, 1, 0. Good, awesome, guys. Okay, else if x is less than y, then comp is going to be, what is going to be the combination now? 0, 0, 1. Okay. Now I took this example from some book, so I can just modify a little. If okay, else we can just, you know, have all three at zeros, which we had initially. So okay, and then we say end module. Okay, perfect timing, 49. So this is a code for a competitor. I actually had one more example, and it's actually a very interesting one. I would like for you to do it at home. It's very simple compared to what we had done today, but I really suggest you to do it at home, you know, and come up with a code. Don't forget to watch the pre-lab video, guys, and also make sure you get all the lab part done, the pre-lab part done. I'll see you guys tomorrow. Thank you for coming.